Well, hey guys, welcome back to the bench. Going to take a look at this switch mode voltage regulator. It's the buck type, meaning you put in a voltage and you'll get a lower regulated voltage output. Handles up to 5 amps. Input voltage range is 8 to 36 volts. Output voltage range is 1.2 to 36 volts as well. Though realistically, I think the range will be a little bit smaller. And of course it has to be less than your input voltage because it is a buck type regulator. Got this from Investia Mall for $2.49, and it's something I bought a little while ago, and I'm just getting around to reviewing it. So we'll check this thing out and see if it's worthy. Let's take a quick look at the theory of operation. I have a simplified schematic. So what you have is your DC voltage coming in to the IC, and inside there's a transistor that switches on and off and chops the output into like a square wave. And it varies the duty cycle of that square wave depending on the voltage and current that we need. On the output is a filter choke and capacitor, which cleans up those pulses and makes it a nice DC. You also see this diode here. In this case, it's a Schottky Diode. When the output goes low, the magnetic field that's built up on this coil collapses and creates a large voltage spike. And the current will flow around like this and forward bias that diode. You see, when the output is high, this diode is reverse biased and does not come on. But when the output goes low and the magnetic field collapses, you'll get current flowing like this, forward biasing this diode. It's called a flyback diode, freewheeling diode, even an efficiency diode. We're actually putting to use that energy, so it helps make the regulator more efficient. Another thing it does is help protect the regulator from that voltage spike because it's conducting. If you've ever seen a solenoid coil or relay coil, sometimes they put a diode in reverse bias across it. What happens is you might have a transistor circuit or some other driver circuit energizing this coil. So if this is the positive side, current would flow down through the coil. Of course, I'm using conventional current flow. Energize the coil, pull in contacts, or pull up a plunger if it's a solenoid. The diode is off, it's in reverse bias. When current is cut from this coil, the magnetic field that's built up will collapse and produce a large voltage spike, which can damage the device that's driving it. You know, it could be a transistor, some sort of logic chip or something. But when that diode's there, the field collapses and conducts and prevents a large spike from being produced, which could damage it. As a matter of fact, in the video description, I'll put a link to a video that was put out by Linear Technology, made by the late great Jim Williams, who talked about how the wrong type of diode selected here could actually result in a spike because the diode not turning on quick enough and damaging the regulator IC. The switch mode chip they're using is an XL4015. Why in the heck is the screen pulsating? Here's some features about it. This is what I talked about earlier, 8 to 36 input voltage, output, high efficiency up to 96%, and well, if you want to read all this stuff, just pause the video. I never heard of this company, XL Semi. Here's the inside block diagram of the IC. Yeah, there's a lot of things going on and what you would think would just be a simple regulator. Here is the actual schematic of the 12 volt 4 amp regulator. At higher output voltages, you don't get as much available current, so Looks like we're using 4 amps here maximum, but with a lower voltage like 5 volts you can get the full 5 amps. One thing you might have been asking about, if that magnetic field collapses and it puts that diode into the circuit, travels through the capacitor, through the diode, wouldn't that affect the output voltage? Well, what's going on here, you have negative feedback. You have your negative feedback divider network. It sends a sample of the output voltage back into the IC, depending on the divider network, which you use it to set your voltage. And the chip adjusts the pulse width to get the proper output voltage. Here is the efficiency at 5 volts using various input voltage levels. You can see it goes pretty high, but then it kind of tapers off close to 85%, even below that with this curve here. But at 12 volts, using various input voltages, it's much higher. And the reason for that is because the ratio of power lost in the circuit versus the total power output it can deliver is much greater at lower voltages. So for example, at 12 volts 4 amps it can put out 48 watts, and we'll just pick a number and say it dissipates 3 watts. There's 3 watts of loss in the circuit. At 5 volts 5 amps there's only 25 watts of output, so that 3 watts is a greater percentage. So that's why you're losing more energy there. What are some of the sources of loss in a switch mode regulator? Well, for one thing, the circuit needs a little bit of power to operate. So there's a small amount there. It uses a MOSFET switching transistor. It'll have what's known as RDS on, or an on resistance. And several amps flowing through that will generate heat or power lost. So that's why the IC here needs to have some thermal dissipation. There'll be some loss in the coil, a little bit of resistive loss in the copper wire, and a little bit of loss in the core material as well, but relatively small. There'll also be some loss in the diode. You have that forward voltage drop. They're using a Schottky, which means the forward voltage drop is lower, but you'll still have that voltage drop with current flowing through that, creating lost power. Okay, well, you probably heard enough of my babble. Let's hook this thing up and see what it does. Okay, so I have some wire soldered up to the little board there. I have this 8 watt 12 volt bulb on the output, and the power supply is on. We're putting in 20 volts, a draw of 390 milliamps. The output is set to 12 volts, and that little bulb is drawing 630 milliamps. The actual bulb rating is probably for 13.5 volts since it's for automotive use, so the power will be a little bit less. So if we do the math real quick, 0.64 times 12, so the bulb is drawing 7.68 watts, and the input power being drawn from the power supply, 20 volts times 0.39 is 7.8. As far as power lost, this coil gets pretty warm, and we're not really pushing this thing yet. The Schottky Diode, yeah, it's not too warm. The chip, barely warm. It's probably getting heat from this coil, that's why it feels slightly warm. But this coil feels the warmest. Hopefully they didn't use some crappy ferrite in the core of that transformer. See if I can put the meter in the shot here. And I'll turn up the voltage on the power supply. What the hell? Oh, let's set it for volts. Okay, I'll rack this thing out to 32 volts. Okay, that's as high as I can take it. And it did increase a little bit, but it's still holding out at 12 volts. Of course, the current went down because, like I said, it's going to keep the power draw constant. And let's see, 32 times 0.27 is, it went up a little bit, 8.64. Let's drop the voltage now and see how it regulates. Okay, so now we're at 14 volts. And it dropped a little bit. And we'll take it down to 12 volts. So it dropped out slightly. One of my meters wants to turn off, but so now it's the same voltage at the input. Now, like I said, these wires are probably losing some, so it's actually probably closer. I need a third meter. I got this one gator clipped on. So what's happening here is, when this doesn't receive enough input voltage, the switch mode pretty much just sends DC on through and keeps that output even. Of course, if I drop down below, I'll drop down to 11 volts now, and you can see here it's dropped out. It's pretty much going to keep it the same. Okay, I'm curious to see a waveform on the scope. Okay, I have the scope on the output of the IC, and again, the output set for 12 volts, the input set at 20 volts, and we have the little light bulb on there. And as I decrease the voltage, you can see the amplitude decrease, and to compensate for that, it has to make the duty cycle, the on time, is longer. And we're hitting dropout 12 volts. So it completely went DC on the output. It shuts it down so it keeps the output voltage as high as possible. So I'll start increasing the voltage again, and you can see it's switching again. And we'll take it all the way up to 32 volts. So the amplitude increased, but the duty cycle went way down because running out of screen there because of the high voltage there. So you can see how the switch mode is actually working. Let me check the output noise. See how much switching signal is getting to the output. These simple little power supplies, I wouldn't think they're anything special at filtering. Pretty darn clean looking to me. Let me set this back to 20 volts. Turn this up. 200 millivolts per division. Where's my oh, what's that way down there for? 100 millivolts per division. So there is some switching noise getting through. But depending on your circuit, you can add additional filtering. For general purpose use, that's nothing serious really. And while I'm thinking of it, I don't know why this camera decided it's not to focus, but the scope says it's running at 185 kilohertz. So yeah, it's pretty close to spec. Yeah, this camera decided it's not focusing. But now I have an issue. I need to try this thing at higher outputs. But looking at those charts, you know, this thing has to dissipate 4 or 5 watts. It could be even worse depending on if they use crappy ferrite in this coil or not. And at that kind of power, this tiny board is going to get sizzling hot. It has to have a heatsink. It did include a little stick-on heatsink. You know, that thing's probably good for half a watt extra. But I need a larger heatsink. So I have to figure out what to do. I think I'll use some thermal transfer tape and stick on a larger heatsink. That way I can try this thing at higher currents. After searching around, I found this heatsink that was small enough that would fit in between the connectors. So I used this expensive 8810 3M thermal transfer tape, $30 per roll. Cleaned with alcohol the board and the heatsink and stuck it on there. So now hopefully I can do some higher power tests and see what this thing can do. This heatsink probably sufficient for up to 6 watts. Should be plenty good for this purpose. Okay, I thought we would push the issue a little bit. This is a 55 watt halogen bulb. And it's been running a while. Yeah, I can hold my finger on that. It's not that hot. Heatsink is starting to warm up. Yeah, I've had it on for a while. The coil's fairly warm. Diode is fairly warm. We're pushing the issue a bit. We're supposed to only go up to 4 amps, but at 55 we'll exceed that a little bit. Let's see here. Voltage is holding out pretty good. Input is 20 volts at 2.66 amps. I'm actually kind of impressed with that thermal transfer tape. Okay, so I finished up the testing. I adjusted the voltage, input voltage, and it kept it locked at 12 volts on the output, even with this 55 watt H3 12 volt halogen type lamp. So we were overloading it a little bit. The thermal tape did its job. It got the heat down into the heat sink. And, you know, during the test I could put my finger on it. So yeah, I think this thing is the duck's guts, like Dave at EEV blog would say. I'm going to use this on my solar panel. The only thing, the included heatsink, which like I said I can't find, but you know, it just sticks on the top here. It's real small. It's not going to do the business at anything over 2 amps. I would certainly put a larger heatsink on it if you're going to use it at, you know, 3 or 4 amps. So another good low cost, you know, $2.50 Investia Mall product. I give this one a thumbs up. Well, that's it. Thanks for watching.